Hello and welcome to CEN 4801. In this session, we are going to address the architectural frameworks and operating environment, uh, which is based on the last session that we addressed, the characteristics, attributes, and properties. Now we understand the system more. We understand the main characteristics of that system, but we need to translate that into more conceptual model, something on paper that we can understand more, and we can identify the elements. We can draw the elements and their interaction between each other. So what's the uh, system architecture? Actually, it's just a structure and framework that supports and enables the integrated components of the system to provide the system's capabilities and perform the missions. Um, it's just an abstraction or graphical representation of the system components and their relationships. In addition, we are going to look at the principles governing that, the policies, the rules that will strict the system or constrain the system, and the system will be working within. All these systems, any system that we are dealing with, will be uh, actually interacting or within an operating environment. So also we need to look at the operating environment that surrounds that system and also include it in our abstraction. The system survival within the operating environment depends on system capabilities, the physical properties, the characteristics, and also the strategies, tactics, and security, timing, and a little bit of luck. This is like a top level system architecture construct that will show me the system of interest interacting with the operating environment, and this applies to any natural or man-made system. It has almost the same construct when we are talking about the high level, so we can consider that as a template that describes a system's relationship to the environment. When systems interact with their operating environment, there are two types of behavior or patterns that emerge. The first one is that systems interact with the dynamics of their operating environment, and that is considered as a peer-to-peer interaction. That means, an element to an element or a subsystem to a subsystem interaction. So that's considered as a peer-to-peer, one-to-one interaction between two systems. The other one is when the system responds to products or byproducts or services and internal failures, which sometimes result in adverse or catastrophic effect. And that will affect the stability, of course, of the system. It might damage or degrade the performance of that system. And we are talking about the survival of that system. If they could not actually survive within that environment, then they are at risk and that system could collapse. The two types of interaction that we can identify, either hierarchical, which comes in vertical interaction under the command and control of higher order systems, or the peer level interaction, which we talked about uh, 2 slides ago or before, when we said that a system to a system or subsystem to a subsystem or element to an element interaction, and that's considered the peer level interaction. The uh, system component concept is important for three reasons. Um, we need to develop that graphic representation because it enables us to organize, classify, and bound system entity abstractions and their interactions with each other and with the environment. It's an architecture that establishes a common framework for developing the logical and physical system architecture of each component within that hierarchy. And it serves as an initial starting point for allocations of multi-level performance specification requirements. We are identifying initially the elements and sub-elements that will be working together to achieve the main mission of the system. So based on that, we can identify the requirements for each system or subsystem. In addition, we can identify the specifications that's needed or that should be allocated in that subsystem or in that element to serve or to achieve the main mission. So the system component interaction can be characterized with two types of relation, the logical and physical. There are two steps in logical component relationship. The first step is to recognize that a relationship does or will exist between components. We know that there is a relation. Now, how that relation is, or the interaction, how does it go? That is the next step where we start looking in details at what type of relation exists between the two. When we assemble the logical component into a framework um, that describes their relationship, we refer to the diagram as a logical architecture. And it should look something like this. So we know that there is a logical association between the light and the person in a room. Um, and we know that once we turn the light we can see the person, and that's due to illumination. But what is the detailed relation between them? We know that the light can be controlled by that person in the room, which is through a switch, and the switch will uh, turn the power source, and the power source or the power will go to the light, and the light will illuminate, and that's how we see that person. So it's like a relation between different entities within the system, so it will achieve a certain goal. And that's what we call logical. It's logical that we could see the person, or there was illumination because there was a light source, but that light source got the power from some place, and so on. We track it until we get to the source of the or the person that triggered that light. The physical implementation of system component interfaces requires more in-depth analysis and decision. Uh, and again, our mission here is just to graphically develop that, to understand how the physical implementation of an interface can be represented. So as we select the components, like maybe look at the logical design and what's needed to make that happen, we can look at the components or the physical components that should be included. And we can identify like a copper wire. We can identify light switches, lighting fixtures, and so on. So those are considered as a physical component of that system. With that being said, then we can develop what we call a block diagram or system block diagram that will show us the physical relationship between the different components. These diagrams becomes the basis for the physical system architecture, and it should look like something like that. So at the beginning we have the logical representation, which is the light source and the human, and we know that there is a relationship between them, and the relationship is the illumination from the light to the human, and the human turn on the light, but we did not look at the physical representation. So going to the physical representation, now we know that there is a light switch, but there are wires that's been connecting or that connects the different parts of the physical system, which will take me to the light bulb, and the light bulb will illuminate on the human. So now we have power source, the wires, the light switch, the building structure, all that within the building structure, and we have the receptacle and the light bulb where it illuminates. And those are the physical parts, or can be considered as the physical representation. Now you can see that we have the dotted line and we have the straight line. And the straight line is electrical relationship. So we are actually identifying the interaction between the different parts of the system or different elements. And then we have the mechanical relationship, and that's the dotted line. So we know that the light switch is within the building structure. The light receptacle is within the building structure, the power source within the building structure. That's mechanical relationship. But with the power source, the wires, the light switch, we have more of electrical relationship that will show how they interact with each other. One of the first tasks as a system analyst or system engineer is to establish a semantic frame of reference for your system of interest. Why do you need to do that? Because what you see in the system maybe it's different than what another person see in the system. Now notice that we have different people that will be interacting with the system, and each one of them will be looking at the system from their own point of view. So the uh, observer, um, we consider that as a frame of reference that will show me, or that will define how the system interacts with other systems, and how the subsystem interact with each other based on that person's point of view. One of the key issues is to understand the system of interest context within the user operating environment. If we need to identify the system user, and we are saying that, okay, who's the user in this case? If we look just as an example, one of the examples, just a computer system that will give us an like a picture, or it will depict how we look at the user. You can see that the word user can be identified in different ways or different point of views, and again based on the reference point of reference that we talked about. So we have the day-to-day operator of the computer system. We have the maintenance personnel. We have personnel who receive work products generated by the computer system. We have trainers who provide hands-on instruction to the operators. And we have electronic mail recipients. So those are different users that use the system, and each one of them will look at the system from their own point of view. And we need to understand that concept, or that interaction. So when you say you are delivering a system for the user, you need to know to which user are you referring, and you need to consider each one of these users. What do they need? What kind of functions? What kind of requirements? And include that within your system. Some organizations establish a contextual frame of reference convention for a system to facilitate communications about specific components within that system. It will be identified, known to know exactly what kind of components and how they interact with each other. Now, the intent is to designate a reference point for the deliverable system. In this way, we can employ different levels or different tiers that will show me the semantic of that system. And the abstraction will look like this. So we have um, like in level one we have the system level, and then we have the subsystems or segments, and that will be level two, and then the products within that, within this those segments, and that's level three, and then subsystems of the product, and that's level four, and then assemblies and sub assemblies, and then parts and so on. So we can divide the system into different levels, and those each one of those levels will have its own requirements, its own specifications, its own attributes and characteristics, and could be identified. And then we can identify even the interaction between the different levels to understand how it will move from one level to another. The system structure or structures are viewed from the point view of system engineer as first analytically as top-down hierarchical decomposition or expansion, and from a physical point of view as a bottom-up vertically integrated sets of components. So either we can look at, actually we need to look at both sides, which is the analytical and the physical, and understand how it can be done. So for system composition, component relationships enable us to analytically decompose the hierarchical system into manageable design levels of complexity, and that will assist me again in knowing the exact interaction with the different subsystems or elements or parts, and the specification for each one of them. And this is an example of a decomposition and the integration of the different elements. So again, we can look at the system, the segments within that system, the products, the subsystems, assemblies, sub-assemblies, and parts, and we can see how they integrate or they work with each other through different relationships. What kind of relationship exists between each one of them? How would they interact with the higher level of the system? And then at the end, we need to understand how all these parts participate in the interaction with the system and the environment. That will be all for this session. Thank you and have a great day.